In this video, we're going to be looking at multiple linear regression and some of the output that SAS gives us from a multiple linear regression. This is the same data set that was used previously to examine how we transform data. And at that point, we got to where we needed a log-log transform, that the log of the cancer volume is the log of the PSA. And here we want to add some variables to this model. So maybe we can add weight, age, BPH, and Gleason. I just threw in some variables to add there, just to get a bigger regression with more variables in it. I'm going to scroll up here. Now normally I would be checking the fit diagnostics, but at the moment all I'm really interested in is the parameter estimates. So I want to go through this table to show you what all of these things mean, especially in the context of multiple linear regression. Here we have our intercept, parameter estimates negative 2.87. The log PSA, or the slope of the log PSA, the slope for weight, age, BPH, and Gleason score. If we look at this model, we see that the log PSA is statistically significant and nothing else is. Now that may be a function of the fact that these variables may be highly correlated. They may also be in the model, or just the presence of one of these in the model may render the other ones not statistically significant. You also see negative coefficients on weight and BPH. It really doesn't make sense that weight might affect cancer volume, but it was there, so I threw it in the model. Again, we have to kind of use our heads as to what variables we put into the model. So looking at these, remember that when we interpret these variables, if I were to write down this equation, it would be negative 2.82 plus 0.685 log PSA minus 0.002 weight plus 0.021 age minus 0.044 BPH plus 0.194 Gleason. Also, we have to remember that when I interpret these coefficients, I have to interpret them in the fact that these other ones are in the model. These values will change if I take one out of the model. So let's just go ahead and do that. Let's take weight out of the model just to see how things change. And we have, just kind of scrolling past the diagnostics, they look better. Well, we see now that the statistical significance level on BPH has changed. It's still not statistically significant, but it is different than it was before. Log PSA hasn't changed that much. The intercept actually hasn't changed that much. Let's see if we can go ahead and find these. So the intercept for the previous model was 2.87, log PSA 0.685, the age was 0.02, and BPH was negative, remember, and Gleason was 0.19. So if I look down here at these coefficients, I see that we have some changes as we did before, from the previous model, I mean. What do these coefficients mean? If the slope changes every time I take a variable in or out of the model, or put one in the model, that means that we have to interpret these slopes in the light of what's already in the model. So log PSA, for example, this slope indicates that for every 1 unit increase in log PSA, the cancer volume will increase by 0.68 units, given that age, BPH, and Gleason are held constant, or they are controlled for in the model. Nothing else is controlled for. So I have to interpret each of these slopes in the light of the fact that the other slopes are in the model. And if I remove another one, I'm going to go ahead and remove BPH. These residuals actually look really good. So if I remove BPH, then again, I have a different slope, a different intercept, a different slope for the age, a different slope for Gleason as well. So taking a variable out of the model changes the slopes that are estimated for the rest of the variables. Therefore, when we interpret our regression model, we have to make sure that we interpret the slopes with the fact that the other variables are controlled for in the model. So in this case, this slope is only controlled for the presence of age and Gleason. Likewise, the slope for age is only controlled by the presence for log PA and Gleason, and the slope for Gleason is only to be interpreted in the fact that log PSA and age are in the model. Let's take a look at how we test for a linear combination of coefficients in a multiple regression model. One of the first tests you'll always see when you have an output of statistical software is what we call the overall F-test. This test is meant to decide whether or not the model itself is statistically significant. In other words, we're testing simultaneously to see if all of the slopes in the model are equal to 0 versus the alternative that at least one slope is not equal to 0. The test statistic for this particular test is our regular old F statistic, which is just the sum of squared regression divided by the degrees of freedom for that particular model, divided by the sum of squared residual and its appropriate degrees of freedom. In other words, we're looking at the mean squared regression, or the mean squared that's due to the model, divided by the mean squared residual, or sometimes also called the mean squared error. We've seen this same sort of test in analysis of variance, but this is just the regression equivalent. We could write this statistic, however, as a ratio of R-squares, where we're looking at the R-square for the entire model divided by 1 minus R-square and its associated degrees of freedom. If we form it in this way, we can see how R-square itself would be a measure of how well the model is fitting the data. Now for each predictor, we have a test for each predictor also. For each predictor, the null hypothesis is that particular value of the slope. So when I say predictor, what I actually mean is that there's a slope associated with each explanatory variable in the model. So what we're really testing to see is if beta I, where I could be any of the predictor variables, I going from 1 to however many predictor variables there are in the model, equals to 0. And of course, the alternative hypothesis is that that particular slope is not equal to 0. Each of these is a different t-test, where the t-statistic is just the parameter estimate or the coefficient estimate divided by the standard error for that particular slope. These are all given in a regression output. And we also need to calculate, well, the standard error beta also has its own calculation. We've seen this before when we were doing simple linear regression, and it really doesn't change now, except the only thing we have to remember is that we have I predictors instead of just the one predictor. As an example of this, let's look at the effect of age and weight on systolic blood pressure. Here we have the data, and we entered them into SAS, and we obtained a scatterplot matrix and the output from PROC-REG, or the regression procedure in SAS. Here's a scatterplot matrix. I like to look at these because this is a really good way to determine whether or not you have linear relationships among the various predictor variables and the response variable. So obviously, if there's not a linear relationship between a predictor and a response, that would indicate that that predictor probably doesn't belong in the model. Likewise, we also would like to see not that strong of a linear relationship between the two predictors. Again, we don't want to have two predictors that are basically telling us the same thing. So if they're highly correlated with each other, they're redundant. If we look at this particular matrix, what we see across the top row is age. And if you look at the very top, you see the words age, weight, and SBP for systolic blood pressure. You see in the age versus age square that we have a histogram. This is just a univariate histogram for the data, indicating whether or not, or giving us an idea, I guess, of whether or not age is distributed normally. It's kind of hard to tell from a histogram, and we have to remember that these are only 30 variables. Histograms are highly dependent on how we define the intervals, but this one doesn't look too bad. We can also look at the age. So the next plot is age on the vertical axis and weight on the horizontal axis. We can see that there's a very strong relationship between age and weight, which might be a problem later on, because these two might actually be too closely related for each one of them to predict differently from the other one in terms of looking at systolic blood pressure. When we look at the relationship between age and systolic blood pressure, again, we see something that looks like a positive linear relationship. Going down to the next row, we have weight on the vertical axis and age on the horizontal axis.
Again, we can see that there's a positive relationship between these two. The histogram in the middle shows that weight looks pretty much normally distributed. And we see on the right side of the middle row a description of weight on the vertical axis and systolic blood pressure on the horizontal axis, again indicating that there is a strong linear relationship between weight and systolic blood pressure. So at this point, it looks like that age and weight are both good predictors of systolic blood pressure and probably should both be included in the model. But let's look at the significance test. So from the output, we have this analysis of variance table at the top. And by the way, we see that we have this mean squared error in the table. It's 1,346. If we take if we divide that by the associated degrees of freedom, which are 27, and take the square root, we get our estimate of the regression standard deviation. That's the estimate of the constant variance that should be for all response variables for all values of x. If we look at the table at the bottom, we have our parameter estimates and all associated hypothesis tests. So really, we don't have to do too many calculations as long as we have statistical software. If we look at the row for age, which is the middle row, we can read across and see that we have our parameter estimate, our standard error, and if we divide the parameter estimate by the standard error, we get the t-statistic value. The next column tells us the p-value for that particular t-test, and in this case, it's 0.0001, which indicates that age is a highly significant predictor of systolic blood pressure, if we include weight in the model. And that's the key to when we interpret regression tests with more than one explanatory variable. We have to remember that these are going to change when we add or subtract variables in the model. So just because we have a significant p-value for age when weight is in the model does not necessarily mean that age by itself is a significant predictor of systolic blood pressure. It might only be so when weight is included. The next column is the standardized estimate for the regression equation. This is just an estimate of the slope when we standardize all x variables and the y variable too. We also see the squared semi-partial correlation and the squared partial correlation. These are correlations that relate to how the particular age variable in this case performs without inclusion of weight in the model, and they are calculated in different ways. Then we have finally the 95% confidence limits. 95% confidence limits for age are from 1.18 to 3.13, which again indicates that age is a significant predictor of systolic blood pressure because we see that 0 is not included in the model. Now, if we look at the last row of the table, we see the very same answers for weight, and they are interpreted analogously. So from the regression output, we can pretty much get all we need in order to determine whether or not predictors are significant for the response of interest.
Let's look at prediction in multiple linear regression models. In a multiple linear regression model, remember that we have yi, our response, equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k all the way up to xk, all the way up to however many variables that we have. And each of these regression coefficients are estimated simultaneously. Suppose we want to have our regression model. We have the estimated parameter slopes. We have all of the estimated errors that we need, and we want to make a prediction from that model. Predicted values are the same as estimated means, and we can calculate those by evaluating the estimated regression at the desired explanatory variable values. Any error in prediction comes both from the error in estimating the population mean and the error inherent in the fact that the new observation differs from its mean. This is just like simple linear regression. Up to this point, other than the fact that we're plugging in multiple explanatory values multiple values of the explanatory variable, I should have said, into the equation, nothing's changed from simple linear regression. So let's look at an example. For quantitative variables, we have this example where this is some data that was gathered on the cost of a hospital stay. And for particular variables in the model, in this case, we had the duration of that stay, which is DUR in the table, the age of the patient in years, and ER visit in the table. That means the number of visits to the emergency room during that hospital stay. Now, these data are actually calculated as the log cost of the response. So the cost is the response variable, and we went ahead and calculated that we calculated the model with cost on the log scale because of considerations involving outliers and other residual plots that were done. So you'll just have to trust me on that. So we're going to calculate the log cost for a 50-year-old individual who stayed 18 days and had 3 ER visits. So the predicted value for the response, in this case the log cost, is equal to 6.168. Now that's the estimate of the intercept in the table, plus 0.0057 times 18. So 0.0057 is the slope for duration, the estimated slope for duration, minus 0.0247 times 50. That is the estimated slope of the regression
0.0247 is the estimated slope for age, times plus 0.1926 times 3, where 0.1926 is from this table as the parameter estimate for the number of ER visits. When we work all this out, it works out to be 5.61, but remember that's on the log scale. So how would we interpret that value? Well, we would raise 5.61 to the e power, or rather, I'm sorry, we would exponentiate 5.61, so it's e to the 5.61, and we would get 274.07. So the true cost, or the regular cost on the original scale, would be $274 per day, I might add. Now, how do I get prediction limits for a prediction from a multiple regression model? We would have to calculate the standard error of the prediction, and we'd have to do so with all of the variables in the model. Now, this is a very hairy task, because now we're talking about multiple coefficients in the model. In this case, we're talking about 3 coefficients in the model, and we need to be able to calculate the prediction limits and the standard errors based on all of those 3 variables. So what we have to do here is really to rely on software. There's a bunch of matrix algebra and algorithms that are behind the scenes in being able to calculate these prediction limits. So here's an example of some output of prediction limits from SAS. CLM and CLI. The CLM is the confidence level for the mean, and CLI would be the prediction limits for an individual value. That's what SAS calls those things. Just for the first 15 observations from the blood pressure data set. This is a little simpler data set, but SAS can handle any number of explanatory variables. So if we look at these, we see that looking at these columns, let's highlight observation 4, just to talk about one specific observation. And all of the other columns are obviously going to be the same, just for different, all of the other rows are going to be the same, except for the fact that they represent different variables in the model, different observations in the model. So for observation 4, our dependent variable, meaning the observed value of y, is 127. The predicted value, meaning the value that's predicted from the linear regression equation, is 102.9217. And we can see, if we skip over to the last column, we can see that 127 minus 102.92 is 24.07, and that's our residual. So that's our observed minus predicted. Going back to the third column, SAS has calculated the standard error prediction, 11.70. So this is the standard error that's going to be used to calculate the confidence limits for the predicted mean and the confidence limits for an individual prediction as well. Now if we go back up to the top row of the table where the words are, and we look up 95% confidence level for the mean, that's what these next 2 columns represent. The first value in row 4, 78.9, is the lower level, the lower endpoint of the confidence interval for the mean response of all possible responses when the explanatory variables the particular explanatory variables are the same as the ones that were used to calculate this predicted value. So the lower limit is 78.9 and the upper limit is 126.93. So in 95% of all samples, we would expect that the mean of all possible responses would be between 78.9 and 126.93. The next 2 columns are the 95% prediction interval. The prediction interval is the prediction of an individual value that has these values, given these values of the explanatory variables. This prediction interval is 23.89 to 181.94. So we're 95% confident that a single individual would have a response, an individual response in between these values. Now just note if we look at these 2 intervals, we see that the confidence interval for the mean prediction is much narrower than the confidence interval for the individual prediction. And this makes complete sense because it's much easier and there's much less error associated with predicting a mean than there is with predicting an individual observation. We've already examined the significance test for overall regression model with any number of predictors. The null hypothesis for that test is that the multiple correlation coefficient, which we call R, is equal to 0, which is the same as an overall analysis of variance. And the alternative hypothesis is that R is not equal to 0, or at least one slope does not equal to 0. The test statistic is our F-test, which is the mean squared regression divided by the mean squared residual with k and n minus k minus 1 degrees of freedom. And our effect size can be R or R squared or the adjusted R squared. Now note that this omnibus F-test procedure is appropriate only for a standard regression. This is where we start, but it's certainly not where we finish. Now let's suppose that we want to test for a certain subset of variables in the model. Let's say that we've run a regression model, the complete model, with all k predictors in the model, and we discover that some of those predictors are not statistically significant when we look at their individual test for each slope individually. So we want to say, let's look at a reduced model with only g of the k predictors, obviously g is going to be less than k in this case, included in the model. This is called a partial F-test. And the null hypothesis here is that the slope belonging to the g plus first parameter is equal to the slope belonging to the g plus second parameter is equal to all of the slopes up to the b kth parameter, and they're all equal to 0. In other words, these extra k minus g parameters in the model are not necessary, or they're close enough to 0 that we can delete them from the model and just use the g predictors that we think are statistically significant. So this is a simultaneous test for k minus g predictors in the model to see whether or not they should be included. And since this is an F-test, and we used our principle of looking at the full versus reduced model, like we did a while back in the course, we're doing the same thing here. Let's look at the F statistic now is a sum of squared regression under the complete model with all k predictors, minus a sum of squared regression under the reduced model with only k minus g predictors divided by k minus g. We're going to divide that by the sum of squared residual for the complete model and its complete degrees of freedom. Let's do an example. The cost of a hospital stay for a heart attack is the response variable in this case, and there are many variables measured. The cost of the stay obviously is the response, the duration of the stay in days, the age in years, the gender of the subject, 0 is male and 1 is female, the number of interventions in the study, so the number of times doctors had to intervene in some way for the patient, the number of drugs prescribed, and the number of visits to the ER. A residual analysis determined that log cost was more appropriate as a response variable. Therefore, everything that we're doing from this point forward is done with log cost as the response instead of the original scale cost. And after a run of the full model, it was seen that only interventions, ER visits, and durations were statistically significant. In other words, we could cut out age, gender, and drugs prescribed, at least possibly cut them out, and it was worth trying to see whether or not we could do this test for subsets to see if all 3 of those variables could be excluded. Here's the SAS output. We look at the full model output from the analysis of variance piece of the regression output versus the reduced model output. So the full model again is the log of cost versus age, gender, number of interventions, number of drugs, ER visits, and duration of the stay. From this we see that the sum of squares for the full model is 1,592.96. The sum of squares for the error is 1,208. If we looked at the reduced model, which is log cost versus the number of interventions, the number of visits, and duration, we see that the sum of squares for that model is 1,523.92, and the sum of squares error for that particular reduced model is 1,217. So putting all of this into our formula for testing the subsets of variables, our null hypothesis is that the slope for age equals the slope for gender equals the slope for number of drugs, and that those are all equal to 0. So if we put all this into the formula for the F statistic, the comparison of the complete model versus the reduced model, we have the following equation with all the numbers included. And that turns out to be an F value of 1.946. The p-value for this particular F with 3 degrees of freedom and 781 degrees of freedom. This is a very large data set, so we have 781 degrees of freedom for the within sum of squares, or the residual sum of squares. Anyway, the p-value for that is 0.12. That's a large p-value, therefore we would not reject the null hypothesis, and we would conclude that it is safe to leave these particular variables out of the model and still have a very good prediction of log cost.
For this video, I would like to just again point out some of the features of the SAS output that we have when we do a multiple linear regression. This time we're looking specifically at the analysis of variance table and the parameter estimates table. I have here the prostate cancer data again, and we have the log cancer volume equals log PSA. I put in this variable capspin and the Gleason score, and I have this option here that you can see, the CLB. What does that do? That gives me confidence limits for the slopes. Go ahead and run that model. The residuals actually look pretty good. They look normally distributed, pretty much around 0. And I just want to scroll up to the top to what we call the analysis of variance table. Just like we did for analysis of variance, where our factor was categorical and we that the explanatory variable was a factor that was categorical and the response was quantitative, here we have a quantitative explanatory variable, well, 3 of them actually, and one quantitative response variable. These can still be broken down into something akin to between and within sums of squares. Here we need this, we're calling it the model or the regression sum of squares. So this is the sum of squares that's actually due to the regression line. Here is the error sum of squares. So this is our residual sum of squares, or the observed minus the predicted sums of squares. And here we have the total sum of squares, which is just looking at every observation, subtracting off the mean and squaring those observations. Every value of the response, I should say, subtracting off the mean of the responses and looking at the square of that. Here's our mean square error, or I'm sorry, a mean squared model, just like we had before, 82 divided by 3. This is the mean squared error, which is 50.5 divided by 93. My F value would be 27.6 divided by 0.54 for a highly significant statistical for model. So this is what I call the overall F-test, or the overall analysis of variance test. It tells me that these 3 variables that I put in the model, log PSA, capspin, and Gleason, are statistically significant for predicting the log of the cancer volume. And here's my R-square is 0.62. It's a fairly high for a small data set with, that's actually a real data set. The adjusted R-squared is adjusted for the number of variables in the model. So remember, R-squared goes up as we add variables to the model, add predictors or explanatory variables to the model. So this is a penalized R-squared, penalized for the fact that there are not just 1 but 3 explanatory variables in the model. Here is my parameter estimates table, and you see I have the confidence limits, just like I asked SAS to do. I just want to show you how these are related to each other. Here's our intercept, negative 1.15, and our t-value for that is negative 1.48. So this column here gives us the standard error for each one, and so if I take the parameter estimate, divide it by the standard error, I get the t-statistic. And you can see that's true for each one of these. So this is beta hat. Here is the standard error of beta hat, and here is the t-statistic. So the quotient of these two gives us the t-statistic. This p-value is determined by looking at a t-statistic, looking at the t-distribution with degrees of freedom equal to 93. That's the error degrees of freedom. And we see that this p-value is very small, less than 0.0001. Now these confidence limits are 95% confidence limits. So these are determined using the t-critical value, not this t-statistic, but the t-critical value for a t-distribution with 93 degrees of freedom. That gives us the positive and negative t-critical value that gives us 95% of the area under the t-distribution with 93 degrees of freedom in between those values. So these confidence limits are not based on this t-statistic, they're actually based on one that is calculated from the t-distribution itself. And this is just beta hat, plus or minus that t-statistic from the t-distribution times the standard error for each one. So you can see if you look at these confidence limits, these do not include 0, again indicating that the null hypothesis that beta for log PSA equals 0 is rejected. That this is also another way to look at that p-value right there says that we would reject the null hypothesis for the test that log PSA is equal to 0, the slope of the log PSA equals 0, I should say. We also reject the null hypothesis that the slope for this variable is equal to 0, and we do not reject the null hypothesis that the slope for Gleason is equal to 0. You can see that this confidence interval contains 0. Again, another indication that 0 is a probable value for beta hat for the Gleason score. Therefore, it's likely not to contribute very much to our understanding or our prediction of the log of the cancer volume.
R-square is a measure of effect size for simple linear regression as well as multiple linear regression. And remember, the interpretation of R-square is the proportion of variance of the response that's explained by the combination of the variables that are in the model. There are two ways to calculate R-square for a multiple linear regression. One way is to find the correlation between the observed y and the predicted y and square it. This is often called the multiple R-squared in software output. Another way is just to work out the partition sums of squares to find the sum of squared regression and sum of squared residual, and then R-square is just the sum of squared regression divided by the sum of squares total. We've seen this definition before when we looked at analysis of variance as well. So R-square is pretty much calculated in the same way, regardless of the model that you're looking at. Now the overall F-test involves R-square as well. We can rewrite the test statistic for the overall F-test using R-square. What does that mean about R-square? Well, it's a measure of goodness of fit, but it also means that the overall regression test, when we're looking at does B0 equal B1 equal B2 equal B all the way up to K, are all the parameters equal to 0, that's equivalent to just testing whether or not R is equal to 0. Now, one of the things about R-square that's a little bit funny and why we don't use it actually as the measure of effect size for a multiple regression model is that the more predictors there are in the model, the larger R-square becomes just because you're adding more predictors to the model. So you're taking away degrees of freedom as you do this, and therefore R-square can become larger than it needs to be. In fact, there's a point where you can totally saturate the model, and you can have an R-square of 1, even though some of your predictors are not actually statistically significant. Predictors may not be adding anything more to the model just by their inclusion in the model. So we want to be able to find a model that what we say is a parsimonious model. So parsimony is this principle of getting the simplest model that gives us the largest R-square. And sometimes we will sacrifice a couple of hundredths in R-square just because that means we can delete an explanatory variable or two and get a simpler model. So also though, a better way to measure effect size in multiple linear regression is to look at what we call the adjusted R-square. The adjusted R-square adjusts for the number of predictor variables in the model. So it penalizes the addition of predictor variables in the model because we know that more predictor variables means a larger R-square. So the formula for the adjusted R-square is just 1 minus R squared total times this penalty term that's n minus 1 divided by n minus k minus 1. So it penalizes for the sample size. So smaller sample sizes will mean a larger adjustment on the R square, which will mean a smaller R squared adjusted as compared to the true R square. Also, this term penalizes us for the number of predicted variables. Again, if we have a small sample size and large number of predicted variables, then we'll have a large adjustment to the R square, and the difference between the adjusted R square and the R square may be somewhat large. But in any case, we would want to use the adjusted R square as our measure of effect size for a multiple linear regression model because it will adjust for the sample size and the number of predictors in the model.
In this worked example, I am going to run some SAS code and get some output, but you are going to explain the results of the output. So I will ask questions as I go along. And then you will submit your answers, put them either in a scanned PDF or a Word document or something like that in order to submit them so that we can look at them later as a class. So the data set I'm using is a data set of 30 individuals. Their ages were given, their weights were measured, and their systolic blood pressure, which is what SBP. So we're looking for relationships among these three variables simultaneously. So the first procedure I want to look at is called proc SG scatter. And SG scatter is for looking at multidimensional scatter plots. Well, it's not really multidimensional scatter plots, but it's scatter plots of more than one variable on an axis. So I want to create a scatter plots matrix of these variables, and I'm also going to put on the diagonal of the scatter plot matrix, I'm going to put a histogram. So when I run this code, I will get, I will get nothing. I will get a syntax error. Diagonal equals histogram. There we go. Ah, that's much better. So we have a scatter plot matrix looking at age on the vertical axis for this row. Weight is on the vertical axis for the second row, and systolic blood pressure is on the vertical axis for the third row. Also in the diagonals, you have histograms of the data, and you also have the horizontal axis is age for this column, weight for this column, and systolic blood pressure for this column. So my question to you is, what does the scatterplot matrix indicate about the relationship between age, blood pressure, and weight? Now, our next thing I'm going to run is actually a proc reg. Same data. Again, there's no reason for me to type that data statement. It's just a really good idea. I want to see how the systolic blood pressure is related to age and weight. It's much easier to calculate or to look at age and weight than it is to look at other things. I'm going to look at the confidence limit for beta, and let's see, that's it. So when I run this, it says it's running. Let me come up here to the analysis of variance table. And you see the output here. Everything looks pretty good. So let's look at these parameter estimates. Your next problem is to write down the regression equation and interpret the value of each slope in the regression equation. And my next question to you is, using this table here, so I'm actually kind of making it a little easy for you because I have to scroll up and down to show you what tables I mean, is the combination of age and weight statistically significant for predicting systolic blood pressure? Now I want you to write down the standard error for each slope. And then I want you to verify for next. I want you to look at the residuals for the model. Let's just look at the residual. Let's scroll down and let's look at this guy. Residuals for SBP, the residual plots for age and weight, and tell me whether or not you think that a linear model is a good fit for age and weight as a linear model predicting SBP, and tell me why or why not.